Imagine for a moment a place in the cosmos so extreme, so utterly bizarre, that it breaks the very laws of physics as we know them. Picture a point in space where gravity has become a tyrant, a force so crushingly powerful that nothing, absolutely nothing, can escape its grasp. Not a spaceship, not a planet, not even a beam of light, the fastest thing in the universe. This isn't the opening scene of a blockbuster science fiction movie. It is a description of a real object that populates our universe. These cosmic enigmas are called black holes, and they represent one of the most profound and mind-bending frontiers of human knowledge. They challenge our intuition and push our understanding to its absolute limits. Let's start with the basics, stripping away the jargon for a moment. At its core, a black hole is a tremendous amount of matter crushed into an astonishingly small space. Imagine taking our sun and squeezing it down until it's no bigger than a city. Same mass, but gravity amplified to an unimaginable degree. Intense gravity is the defining feature. A region of space-time where gravity prevents anything, including light, from escaping. Black hole is a bit of a misnomer. It's not a hole like an empty pit. It's the opposite of empty, one of the most densely packed objects in the universe. The black is accurate. Light can't escape, so it appears dark to our telescopes. The hole refers to a one-way boundary, the event horizon. Cross that invisible line, and you can't get back out. It's a cosmic cave motel. Matter checks in, but it doesn't check out. How do these behemoths form? Start with a massive star, far heavier than our sun. The star fights itself, fusion pushing out, gravity crushing in. When nuclear fuel runs out, the outward push stops. Gravity wins. The core collapses catastrophically. For the biggest stars, collapse is unstoppable. A black hole is born from the stellar ashes. Those are stellar mass black holes, a few times the mass of our sun. The universe also makes supermassive black holes, monsters millions or even billions of times the sun's mass. We think they lurk at the centers of most large galaxies, including the Milky Way. How did they get so big? Did they start small and grow over eons by gobbling up gas dust other stars? Or did they form from direct collapse of gigantic gas clouds in the early universe? The jury is still out. Popular culture has enthusiastically embraced this vision, painting black holes as cosmic whirlpools, gateways to other dimensions. One of the most persistent myths about black holes is that they are cosmic vacuum cleaners roaming the universe and aggressively sucking up everything in their path. Movies love this idea. A rogue black hole enters a solar system. Planets are helplessly pulled from their orbits toward their doom. This makes for a great disaster film, but it's a fundamental misunderstanding of how gravity works. A black hole's gravitational pull is incredibly strong, but only when you get very, very close to it. From a safe distance, its gravity is no different from that of any other object with the same mass. Let's perform a thought experiment. Imagine that, by some magical act, our sun was instantly replaced by a black hole of the exact same mass. What would happen to the planets? The answer, which surprises many people, is not much. The sky would go dark, temperatures would plummet, all life would perish, of course. But planets would not be sucked in. It would continue to orbit the new black hole in precisely the same path it follows around the sun today. The gravitational pull we feel depends on the black hole's mass and our distance from it, not on its mysterious nature. The danger zone around a black hole is actually quite small in cosmic terms. You have to get relatively close to the event horizon before its pull becomes inescapable. For a black hole the mass of our sun, you would need to travel to within a few kilometers of it to be in real trouble. Space is vast, and the chances of a star or planet accidentally stumbling that close to a stellar mass black hole are incredibly slim. Black holes are not hunters. They are passive objects that wait for matter to wander into their immediate vicinity. They follow the same laws of gravity as everyone else. The dramatic swirling disks of glowing gas you see in illustrations are also part of this story. That material, known as an accretion disk, doesn't just fall straight in. Because of the conservation of angular momentum, the same principle that makes an ice skater spin faster when she pulls her arms in, the gas and dust spiral around the black hole, creating a cosmic traffic jam. This process heats the material to millions of degrees, causing it to glow brightly in X-rays and other forms of light. Now we venture into the realm of pure speculation, a place where science fiction writers and theoretical physicists sometimes meet. The idea that black holes could be portals or wormholes leading to other parts of our universe, or even to other universes entirely, is a tantalizing one. This notion isn't just pulled from thin air. It has roots in the very mathematics used to describe black holes. Specifically, Albert Einstein's theory of general relativity. However, there is a giant chasm between a solution that works on paper and a structure that could actually exist in our universe, let alone one that a human could travel through. The wormholes predicted by standard general relativity are incredibly unstable. The intense gravitational forces inside the black hole's event horizon would stretch any object into a long, thin strand of atoms. Spaghettification. If black holes are completely black, how on earth do we know they are out there? It's a perfectly reasonable question, and the answer is, well, a wonderful example of scientific detective work. We can't see black holes directly, but we can see the powerful effects they have on the space and matter around them. It's like trying to find an invisible person walking through a crowded room. You can't see them, but you can track their path by watching how they bump into other people and knock over furniture. One of the most powerful methods is to watch the behavior of stars. They see it, whipping around a seemingly empty point in space at incredible speeds. By carefully tracking the star's orbit over many years, they can use Kepler's laws to calculate the mass of the unseen companion. If that mass is enormous and emits no light, a black hole becomes the only viable suspect. Specialized telescopes catch the high-energy glow of hot, infalling gas, X-rays, and radio waves. Listening to the universe's deepest secrets. For most of human history, our only way of studying the cosmos was by looking at it. We built bigger and better telescopes to capture light, visible photons, radio waves, X-rays. But in 2015, humanity gained a completely new sense. We learned how to listen, not with our ears, but with instruments that detect ripples in space-time. These ripples are called gravitational waves, opening a new window on the universe's most enigmatic events, including black holes. Einstein predicted gravitational waves a century earlier. Accelerating masses should make ripples that race at light speed, like a boat's wake. The effect at Earth is absurdly tiny, far smaller than an atomic nucleus. LIGO overcame the challenge with two 4-kilometer L-shaped observatories. A split laser beam races down vacuum arms, reflects, and recombines. A passing wave shifts the lengths ever so slightly, knocking the light out of alignment. On September 14, 2015, LIGO heard a clear chirp. Two stellar mass black holes merging. In a heartbeat, about 3 suns of mass became pure gravitational wave energy. The first picture, a shadow against the void. For all the indirect evidence, the ultimate prize remained elusive. A direct image. The Event Horizon Telescope aimed to capture a black hole's shadow. Not the hole itself, but its silhouette against glowing gas. Seeing it was like reading a coin's date from across a continent. So they built a virtual, Earth-sized telescope with very long baseline interferometry. Linked dishes from Hawaii to Chile, Spain to the South Pole. Nights of observing, mountains of data. April 10th, 2019. Humanity saw a black hole's shadow. A luminous ring encircling a perfectly dark center. The point of no return, made visible at last. The believers and the skeptics, a necessary dance. Belief and skepticism partner to keep science honest. Most astronomers, convinced by mountains of evidence, say black holes are real. Orbits, X-rays, gravitational waves, the EHT image. For them, the case is closed. Good skeptics don't deny. They probe for weaknesses and demand rigor. They note our laws break down at the singularity. Maybe we need a deeper theory, perhaps quantum gravity. Alternatives are tested head-to-head with data. So far, black holes pass, rivals falter. Belief, challenge, verification. That's what separates science from dogma. The unwritten chapter. What comes next? We've defined black holes, debunked myths, and separated fiction from reality. We learn to find them, listen to them, and see their shadows. Black holes are not portals, not monsters, but extreme outcomes of physics. What happens at the singularity? Where does information go? Next-gen detectors and telescopes will write the next chapter. Black holes mark the endless frontier, promising a future filled with wonder and discovery. I hope you like our stories of the skies. Until we meet again, I wish you a clear sky.